Okay, let's start with video number 8 on basics of bonding. I don't know if you remember from the previous video. Let me show that off right away. We were talking about radical cations and radical anions, right? And so if you can look at it, we looked at what happens when you homolytically cleave a double bond, a pi bond, in ethylene to give you the diradical. And then if you were to remove an electron from the diradical to give you something else, some anion, what remains is a cation, right? I mean, this species becomes a cation, a carbocation. But because there is a radical associated with the carbon next to it, it's not a true cation, but it's a radical cation, right? So if you're confused about this, go back to the previous video. It explains this in detail. And similarly, if you were to add an electron to this system, you get a two electrons on this carbon, which started off with one. The two electrons means a minus charge, right? That's when you got a minus charge. And so you get a radical anion, right? It's a radical anion. A radical anion is a radical that has a negative charge, right? Radical and a negative charge, both. So in some ways, it is important to keep this in mind. So a radical anion, a radical cation are represented sometimes like this and sometimes like that. Radical anion or radical cation, okay? This R is just anything. So with that, let's kind of move to the next topic, which would be the fate of radical cations. For example, why we are interested in radical cations is it is intricately related to the doping of polyacetylene. So let's look at it. So we looked at something like CH2, double bond CH2, giving you CH2 dot, CH2 dot, right? This is the homolytic cleavage that I was mentioning the previous. This is the diradical, which then gets oxidized to give you the radical cation, right? Which loses an electron to give you the radical cation, right? The question is, let's look at it from a very simple perspective. We know that CH2, double bond CH2, plus, say, iodine, right? From organic chemistry basics, what do you get? What do you get with this? If you recall, the iodine is nothing but I. So you've been asked to memorize it as one iodine goes here, one iodine goes here. So you generally are taught this, right? So the double bond is gone and the iodine adds across the double bond, correct? So it becomes, this is sp2, sp2, it all becomes sp3. Remember that? This is called addition across a pi bond, right? Similarly, if you were to take acetylene and add iodine, what do you expect? There are two pi bonds, right? So you'll get this first, right? Triple bond becomes a double bond, but the two iodines are added. And I guess that goes further, right? One more gets added, CH. Correct? So both the double bonds have been consumed by now 2 moles of iodine. So it's called addition across both pi bonds, correct? 2 pi bonds here. We know this from organic chemistry. Now the question is, from what we have learned in the previous video, how do you explain this, right? This is no explanation given in organic chemistry. Now we'll go into details here. So you start off with CH2, double bond CH2. Then you get CH2 dot, CH2 dot, right? This is the homolytic cleavage. If you can view it this way, then I was saying that iodine takes an electron, right, to give you CH2 dot, CH2 plus, right, plus iodide, correct? This is the radical cation. You see what's happening here, right? The iodide is very close to the plus. So this can just, the two electrons from the iodide can just form a bond, right? You can just get CH2 dot CH2I, right? That's one possibility. There's a plus and a minus, so they can just couple to give you a covalent bond. This is an ionic bond. Plus minus is an ionic bond, right? The bond is ionic here. This is covalent. So they've got another dot here. So this another iodine can steal another electron to give you CH2 plus CH2I plus I minus, right? This I becomes I minus. Again, these two are close together, so this can form a bond to give you I CH2, CH2, I. And that's exactly what the product is, right? This is what this is. This is how, which all you had to do is memorize in organic chemistry. Addition across the double bond is actually a series of steps of one electron transfers from the radical to the iodine to give you iodide. Iodide then couples to give you iodine, covalently bond to CH2 on one side, and the process repeats to get iodine covalently bonded to the CH2 on the other side. In effect, in the end, you see that iodine has added across the pi bond, right? So that's how they react. Radical cations react. So suppose you had multiple double bonds, right? Suppose you had something like this. And the last CH is what I'm giving you. This is all double bonds, okay? I'm not drawing the H's. Suppose you had a pi bond at the end of a chain. What would happen? Say maybe you can do the same thing. Say like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So that's a CH2 dot. That's a CH dot, right? Diradical. And suppose an iodine were to steal this, okay, to give you what? Once again, it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? That's a CH2, right? That becomes a plus I minus, right? Very similar to what we saw before. This is a single bond, okay? So it's a radical. Now, what do you think will happen? In the past, we said this just coupled, right? To give you a bond. Right? That's what we said. What do you think might happen here? Because there are double bonds everywhere, this radical and the plus charge can completely delocalize, right? This charge and radical can completely be shared over the entire chain of the, so it's whisked away from the edge. The reactive center is whisked away from the edge. And therefore, this coupling never occurs. So what happens in effect is exactly what you've seen so many times before. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The way I have said it, that this goes that right. This is what it's been whisked away, and and then we put the iodide remains, and of course there's a plus charge, right? There's a plus. So the plus, we put it uh, outside the brackets, and we call this doped CHX. This is how the doped CHX evolves. Now you know from the basics of bonding, the oxidation of polyacetylene, undoped polyacetylene, by iodine to doped is related intricately to the electron dance that comes as a result of a homolytic cleavage. This is one way of looking at it, right? Homolytic cleavage of the bond, the terminal bond or the internal bond, doesn't matter. It doesn't have to be the terminal bond. You can have the internal, you can have this having in the beginning, in the middle of the chain, to give you a dot and a plus here as well, right? It doesn't have to be at the end. I did it at the end to make it easy for you to understand. Since we started with an end over there, so that's how we started it. So now I hope you understand as to how this dot 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 structure comes about. It's the radical cation that itself is stable, okay, at room temperature. Something that is so unstable like this, radical cation so unstable and then collapses to an addition, the radical cation itself is stable, and therefore this is how this is how you explain the high conductivity of polyacetylene, is because this radical cation is delocalized completely along the polymer backbone. Hopefully this is a good enough explanation. We can embellish on this later, but I think for this level it's fine. So let me stop here.